Hello everyone. So in the last video we looked at Gauss Jordan elimination and how it could change solutions, not the solution set, but it's more like um, changes the geometry of the matrix. So when you have inconsistent solutions, you're basically converting the planes to parallel planes, and um, you will end up having an inconsistent solution. But again, it's one way to solve the equations. So that was the last thing we've seen. Um, so the reduced echelon form. So this is an inconsistent solution. As you can see, 0 does not really equate to negative 32. So you do the reduced echelon form. You do that by making sure that there is a leading one here and the row is only zeros, and the same for the second row as well. And in that sense, what you're doing basically, you would produce parallel planes to each other, and the solution will still be inconsistent though, unlike what we've seen with infinitely many solutions. Um, it's easier to solve those using reduced echelon form. Anyway, so I've taken a peek on what we should be expecting up next with matrix. I mean, this is a big topic, and we should be able to get through with this. Now, with matrix, we're working with different equations that we abstracted, as in. So basically, we have different equations. We try to solve those using the matrix. And what we should be expecting next is a set of other interesting things that we could do with matrices, and that's like the addition, subtraction, and all the whole goodness that comes with it. So we've got the multiplication, the association of matrices, and then the whole deal. So what we're doing now is a bit different than what we would be doing in the next set of videos. So anyways, we should keep going with the series that we started off with. So we're still with the set of videos we last stopped at. Yeah, the elimination of things. This is what we've been touching. If we take a look, we've taken.
But considering that this system contained two of the planes and the system became parallel.
As you can see, as we solved for the system, we've got all the.
So why did the planes described by rows 2 and 3 become parallel? When Gauss-Jordan elimination reduces a matrix representing equations which describe a triangular tube, during the reduction process, coefficients of the same variable will be zeroed in two of the equations. So far, we have seen two configurations of planes that will produce an inconsistent system of three linear equations in three variables. However, in three variable systems with more than three equations, there are one common point at the origin shared by all three planes. In that column, adding -1 times row 3 containing all zero coefficient entries and a non-zero constant entry, indicating an inconsistent system.
So what did I say just now when it came to negative 32? I think I've said something. I should probably said it actually.
That a system of linear equations in the system. We will examine different ways that a system of is already a 1. We only need to zero the other is now 0. So we zero the other non-zero entry in.
Oh yeah. So the difference between this example and this example we have a notion is that, as you can see, there's a leading one here, and so we will pivot this to 0.
That column, adding -1 times row 3 coefficient. This technique indicating an inconsistent system.
I'm not sure why he didn't convert this to 1 as well, but what's the deal here?
variable values exist that are consistent with the solutions for every equation in the system. In the previous lecture, we saw that when a matrix representing an inconsistent system is reduced using Gauss Jordan elimination, at some point during the process, a row will be produced with all zero coefficient entries and a non-zero constant entry. In this lecture, we will examine different ways that a system of linear equations in three variables can be inconsistent and how the planes which graphically represent this system change during the process of Gauss Jordan elimination. We have seen that any system whose graph contains two distinct parallel plane equations still describe parallel planes, and just as before, the variable. To find out, let's to add -4 times row 1 as the system which contained parallel Gauss above the leading entry of 3 and row 2. System is inconsistent. At this point, we can stop since we know that the system has no solutions, or we can continue until the matrix is in reduced row echelon form. To do this, we change the leading entry of row 3 to a 1, using a scale operation to multiply row 3 by -1/32.
Oh yeah, of course. I'm not sure why I've missed that. I mean, in this very last example.
In the last several lectures, so we zero the other non-zero entry in that column, adding -1 times row 3 to row 4. This gives us the result that is always produced when a pivot acts on two matrix rows corresponding to parallel planes. A row containing all zero coefficient entries and a non-zero constant entry, indicating an inconsistent system.
Okay, so you just need to know that this is an inconsistent solution. Like earlier when we got the -32 being the inconsistent solution, I'm not really sure why. I still can't get my head over why was it in that example that you tried to change the -32 to 1 to make it a leading one, even though it's like an inconsistent solution, which I'm a bit confused about, really. So let's see.
Coefficient entries and a non-zero constant entry, indicating that this system is inconsistent. At this point, we can stop since we know that the system has no solutions, or we can continue until the matrix is in reduced row echelon form. To do this, we change the leading entry of row 3 to a 1, using a scale operation to multiply row 3 by -1/32.
Which is like weird. Why here? Why do you want to make this a leading one? I'm just confused about it.
The leading entries of each row are now
Well, and in all fairness, it wouldn't really matter because what you
ones. But to be in reduced row echelon form, each leading entry must be the only non-zero entry in its column. We therefore must zero the entries above the leading entry of row 3 and row 2.
Yeah, so basically if you have a variable here, no matter how much you scale it, it's still the same solution set. You have 1, 10, it doesn't really matter. But what I'm struggling to realize or understand is that why did he opt for this option? I mean, why did he opt to changing this to 1? I mean, in this example that we have here, he didn't bother to do so. He just stopped it, at this.
Planes. A row containing all zero coefficient entries and a non-zero constant entry, indicating an inconsistent system.
Yeah, so why does it have to be that is to be in reduced echelon form? Why does this have to be 1? Alright, let's see what he's doing here.
But considering that this system contained no parallel planes, how did we end up with the same type of result as the system which contained parallel planes? Surprisingly, during the process of Gauss Jordan elimination, 2 of the planes in the system became parallel. So why did the planes described by rows 2 and 3 become parallel? When Gauss Jordan elimination reduces a matrix representing equations which describe a triangular tube,
So I think we could safely say, leading 1, I think we could see here, notes that you don't have to always convert now we should do.
hello.
So the thing is here about Gauss elimination is that we try our best to achieve the reduced echelon form, but I'm not sure why in this case, given this is all zeros, is it because there was a 1 on top of it? I think I should ask, I want to ask this question in Stack Overflow, math stack. I think I should. I mean, why in this case did he work on reducing the negative 32 to 1? And for the previous example, he did not. Just kept it as 3. I think I should ask that question. Should add it should add that question now. Pause the video and try to log in and do the rest of the good stuff. So I'm in math stack exchange. I'm asked the question. Now I'm not sure how matrix is. A matrix is. I think I should add images to it, right? I believe I should. But yeah, and then I just link it to this is a link. So the caption, yeah, this is the link. So the video we were watching is this. Oh, this is the traffic flow.
More complicated by adding a y term, not by changing the to a 1 operation to multiply row 3 by negative 1/32.
1057. Okay. Sorry, it's another one. We should get a link here. Share. Start it. Copy. Link. So there we are. And that question is out, so let's see what they say. Now back to what we were doing until this is resolved. This is, we should put this to the side now, and we should start with the
System of equations and eliminate equation. In earlier lectures, we saw how systems of linear equations can be solved using matrices through the process of Gauss Jordan elimination. Using matrices lectures, we saw how systems of linear equations can be solved using matrices through the process of Gauss Jordan elimination. Gauss Jordan elimination is especially useful in systems of more than 3 variables, where the substitution or elimination methods can become cumbersome. But what types of actual applications can be solved by systems of linear equations with more than 3 variables? In this lecture, we will examine one application that can be solved by a system of linear equations with 4 or more variables. This application involves modeling and predicting the flow of traffic through a network of streets.
Now we're talking. You see what he said? Modeling and predicting. You know, predicting in machine learning, that should ring a bell.
Several years ago, the engineering students at YU were asked to analyze the flow of traffic through a traffic circle near the university. They started by making a schematic diagram with arrows showing the direction of traffic flow in, out, and around the circle. They were told that 75 vehicles per minute flowed into the circle from the north, and 92 vehicles per minute flowed out to the east. Realizing that there was a high volume of traffic flowing in from the north and out to the east, the students made a recommendation to reverse the direction of traffic in the circle between the north and east intersections. They also recommended adding a traffic cut-through between the streets on the east and west sides of the circle. Once these changes were made, the students asked the university to take some new measurements. It was confirmed that the original 2 measurements were still valid, plus 2 additional measurements were made. The traffic flow between the west and south streets was determined to be 56 vehicles per minute, and the traffic flow between the south and east streets was measured as 23 vehicles per minute. The students decided that even though there were no traffic measurements for the remaining roads, they would try to calculate the missing traffic flow data. They started by assigning variables to represent the traffic flow on each of the remaining roads. They could then create a system of equations which they hoped would allow them to calculate the missing information. The first equation they created equated the total traffic flow into the traffic circle to the total traffic flow out. They also wrote 4 equations for the traffic flow through the 4 intersections. Traffic flow into the west intersection equals traffic flow out of the west intersection. Traffic flow into the north intersection equals traffic flow out of the north intersection. Traffic flow into the east intersection equals traffic flow out of the east intersection. And traffic flow into the south intersection equals traffic flow out of the south intersection.
X5 plus 23.
This gave them a system of 5 linear equations in 5 variables, x1 through x5. So let's see how this system of equations can be solved to find the values of these 5 unknowns. The first step is to simplify the equations, moving all the variables in each equation to the left side and combining all the constants on the right. The system of 5 linear equations can now be put into matrix form. This matrix is relatively simple, since the variables in the equations all have coefficients of 1 and the remaining matrix entries left of the vertical line are all zeros. The constants in the equation.
Let me pause here for a second. So if you go for a reduced echelon form, so first of all, you could go for Gaussian elimination, right? Gaussian elimination would mean that we would move this one upwards and then have, so we need to suffice a diagonal of ones, and then
A matrix like this, where most of the entries are zeros, is called a sparse matrix.
what?
Now that
Oh, I didn't know that. That's a good thing to write down, I guess.
a matrix like this, where most of the entries are zeros, is called a sparse matrix.
Sure, let's deal with this. I could just have this in there too. It's pretty useful, I guess. Whatever.
Now that the equations are represented as a matrix, that matrix can be transformed to reduced row echelon form through Gauss Jordan elimination. We start by making sure that the entry in the first row and column is a 1. Although that entry is 0, since rows 2 and 3 have 1s in the first column, we can simply exchange row 1 with either one of those rows. To be in reduced row echelon form, all the entries below that leading entry must be 0. Since only one of those entries is not 0, we only need to 0 that one entry.
So, row 1 minus row 2.
We do this using a pivot operation to add -1 times row 1 to row 2. Since all the entries below the leading entry in the first row, to make sure that its leading entry is a 1.
It is.
Since that entry is a 1, we once again make sure that all the entries below are zeros. Since only one of these entries is not 0, we only need to 0 that one entry.
-1 and add it to row 3.
We do this with a 3. Since all the entries below the row, since that entry is a 1, we must now make, once again, there is only a single non-zero entry times row 3 to row 4.
Have a 2 then next.
Since all the entries below the third row's leading entry are now 0, we move to the fourth row, making sure that its leading entry is a 1.
But it's not. It is actually.
Since that entry is a 1, we now change the entry below to 0 with another pivot, adding -1 times row 4 to row 5. Row 5 has now become all zeros. Rows containing all zeros are allowed in reduced row echelon form matrices as long as they are located at the bottom of the matrix.
Fair enough. Should add this note too as well. Just get out it here. Nice to waste the blocks. Just echelon form. If, and only if it is at the very bottom. Now I'm not sure if you have, say, 2 rows at the very bottom that are zeros. I'm not sure how is that going to be solved, but that's that. And we should add the link here. Then it's a bookmark. There's a nice set of examples. Yeah, okay, then that's that.
So the matrix now has 4 rows with leading entries. As required in reduced row echelon form, all those leading entries are 1s, and the entries below those leading entries are zeros. However, every entry above each leading entry must also be 0, and 2 of these entries are not 0. Starting with the non-zero entry in row 4, entry are now 0, the entry above entry with a pivot matrix. Since 4 of the 5 columns left of the vertical line contain a leading entry, there are 4 pivot columns. And since not every column left of the vertical line is a pivot column, this tells us that the system has infinitely many solutions. As we also saw, infinitely many solutions. This tells us that not every column left of the vertical line is a pivot column. This tells us that the system has infinitely many solutions. As we also saw, when writing parametric equations to describe these solutions, the variables associated with pivot columns are treated as dependent variables, and the variable associated with the remaining column is considered to be a free variable. To create the parametric description of the solution set, we first convert the matrix rows into equations so that the dependent variables are alone on the left side. This gives us equations that express the dependent variables x1, x2, x3, and x5 as functions of the free variable x4. We then equate the free variable x4 to a parameter that we will call t, and replace x4 in the remaining equations with t. We now have a set of parametric equations that express all 5 system variables x1 through x5 as either constants or functions of the parameter t. Picking a value for t produces values for the 5 missing traffic flow measurements. The parameter t can vary over any set of values which makes sense. For example, we know that t must have an integer value since fractional vehicles don't make sense. And t cannot be a negative integer since on a one-way street, traffic can only flow in one direction. It could be 0 or 10 or 69. But t could not be 70, since any value for t of 70 or greater would produce a negative traffic flow value for the west to east cut-through street. So the range of values for t that produces reasonable results is positive integers less than 70. Once the matrix representing this system of equations had been transformed to reduced row echelon form, we knew that the system had infinitely many solutions, since not every column left of the vertical line was a pivot column. In particular, x4 was a free variable, which could have many possible values. And as we saw, depending on the value of x4, the calculated values for x1 and x3 varied. So what if we made an additional measurement to determine the actual calculated values for x1 and x3 varied? So what if we made an additional measurement to determine the actual traffic flow at x4? What effect would this have on our system of equations? To find out, let's go back to the simplified equations created from our original traffic model and plug in a value for x4 of 10 vehicles per minute. Now let's see what happens when we solve this system of 5 linear equations in 4 variables, x1, x2, x3, and x5. We first simplify the equations containing more than one constant by combining the constants. The system of equations can now be put into matrix form. Once again, the variables in each equation have coefficients of either 1 model, value of x4, the calculated value. In particular, x4 was a free variable, which could have many possible values. And as we saw, depending on the value of x4, the calculated values for x1 and x3 varied. So what if we made an additional measurement to determine the actual traffic flow at x4? What effect would this have on our system of equations? To find out, let's go back to the simplified equations created from our original traffic model and plug in a value for x4 of 10 vehicles per minute. Equations in contain once again the and the just as before, we will start the to 1. To be in reduced row echelon form, all the entries below that leading entry must be 0. Only one entry uses 2. Since all the entries below the row is a 1, all the entries to the third entry, and we row 4. Entry 4, 1, negative 1, and the matrix has 4 rows with leading entries. As is required for reduced row echelon form, all those leading entries are 1s, and the entries below those leading entries are 0s. So be tree with a pivot, adding 1 times row 3. This matrix 59, and 33 vehicles per minute. This single unique solution allows us to fill in the missing measurements in our traffic model. So far, we have seen how the system of linear equations which corresponds to this traffic flow model can have a single unique solution or infinitely many solutions. So what circumstances could cause this model to produce an inconsistent system having no solutions? To find out, let's go back to the simplified equations created from our original traffic model and plug in a measured traffic flow value of 40 vehicles per hour for x2. Now let's see what happens when we reduce the matrix representing this system of equations. We first simplify any equation containing more than one constant. Now let's see what happens when we reduce the matrix representing this system of equations. We first simplify any equation containing more than one constant by combining.
What's wrong with this crap?
Measured traffic flow value of 40 vehicles per hour for x2. Equations x5 equals 23 and x5 equals inconsistent. However, let's go through the process of Gauss Jordan elimination anyway, just to show what happens. To be in reduced row echelon form, all the entries below that. Since that entry is a -1, we use a scale operation to multiply row 2 by -1. Since row 4 now can, we know that this system is inconsistent, having no solutions. In this lecture, we saw one type of application that can be solved by a system of linear equations with 4 or more variables. This application involved modeling and predicting the flow of traffic through a network of streets. In the next lecture, we will examine another application for systems with 4 or more variables, which involves finding a mathematical function that describes the behavior of a physical system given some number of measured data points.
Interesting. So it was an amusing session. We should be doing more exercises of this as soon as we finish with the next lecture. Yeah, before hitting the quadratic functions and polynomials. So the second thing, after the next lecture, is all exercises and revisiting what we have studied so far. Yeah, I'll see you then.